minutes of the day. In this session, we will concentrate on how to draw a root locus using construction rules. So in this session, we are only concentrating on what are the rules to be followed to construct a root locus. Now, this is the root locus of a system obtained from a MATLAB. But in this root locus, how to draw it manually? That is the question arises. So if we see this graph, here is a one branch which is of red color, start from this point. Here is another branch. Here is a green colored third branch and dark blue color fourth branch. So here the branches is 4. Total number of branches are 4. And it shows that it is from some pole it is starting, some pole and somewhere it is end. These are not the part of the root locus. So how to consider how many branches, where it starts, where it terminates, whether it is intersecting the imaginary axis, and where this breaking of two branches takes place, and so on. So many more questions arises while drawing them manually. So we need to follow some rules to construct a root locus. So what are those rules? So first rule, if you see this graph is symmetrical about a real axis. See, here increasing and symmetrically here decreasing. So this shape and this shape, if you fold about real axis, it looks like a single waveform. So first is that root locus is symmetrical about real axis. So second rule says about the number of branches starting and terminating points. Now consider a system with open loop transfer function g of s h of s equal to k into some p of s divided by q of s, where p of s is a numerator polynomial and q of s is a denominator polynomial, with n open loop poles and m open loop zeros. This means q of s is of order n and p of s is of order m. So now to obtain a closed loop poles, we need a characteristic equation, that is 1 plus g of s h of s equal to 0. So if I substitute this g of s h of s is k into p of s by q of s, by taking the common denominator, anyhow it is a 0, it is 0 only when numerator is 0, that is q of s plus k p of s is 0. So in this equation, how many poles exist? Because root locus is equal to, by the definition, it is the locus of the closed loop poles. So the number of branches is equal to number of closed loop poles. So here the question is, how many poles exist in this equation? So in this order of this system, this characteristic equation depends on open loop poles and open loop 0. This is of order n, this is of order m. So total system order is based on m or n, because whichever is the largest, that is the order of this equation. So if m is equal to 2, n equal to 3, then this equation contains s cube. So the number of poles is closed loop poles equal to 3. That means the number of branches equal to 3. Suppose m is 3, n is 2. Open loop zeros is 3, open loop poles is 2. Then also this q of s is s square term, but this p of s is s cube term. So that this order remains s cube. So the order of this characteristic equation depends on m and n, whichever is the largest. So number of closed loop poles equal to number of branches equal to maximum of m comma n. That is, whichever is the largest, open loop poles or open loop zeros. Now about the starting point. By the definition of the root locus is the variation of closed loop poles as k varies from 0 to infinity. So root locus starts when k equal to 0. So when k equal to 0, what happens to this characteristic equation? This p of s, this coefficient becomes 0. Only q of s equal to 0. So what are the roots of q of s equal to 0? It is the same as open loop poles. So by equating denominator polynomial of this open loop transfer function, it's the same as q of s equal to 0. So closed loop poles equal to open loop zeros. That means root locus starts from open loop poles. So when k equal to 0, root locus starts. That means branches start from open loop poles. Root locus terminating point when k is equal to infinity. Because by that definition, when k is equal to infinity, what happens to this characteristic equation? K is infinity means 1 by 0. Infinity can be written as 1 by 0 by taking the common denominator 0 q of s plus p of s equal to 0. So p of s equal to 0 and closed loop poles equal to open loop zeros. So root locus terminates at open loop zeros. So number of branches, second rule says number of branches, that is max of m comma n, open loop poles and open loop zeros, whichever is the largest, that is much number of branches root locus like this. And root locus starts from open loop poles and root locus terminates at open loop zeros. Now if this m and n are not equal, so that means open loop poles are not equal to open loop zeros. So what happens to the difference branches? N difference m. It may be n minus m or m minus n. Where it will start or where it will terminate. So if m is greater than n, that is open loop zeros are greater than open loop poles, then total number of branches is m, out of which n starts from open loop poles. What about the other branches starts from? Where it will starts? So m minus n branches starts from open loop poles at infinity. Got it? So if m is larger, total number of branches m, but starting point has only n because starts from open loop poles, n branch open loop poles, m minus n branches start from infinity. Similarly, if m is lesser than n is larger. So in that case also number of branches equal to n, but it has only m terminating points. Where will n minus m terminates? So n minus n branches terminates at open loop zeros at infinity. A third point, existence of root locus on real axis. Now on the real axis, which part of the real axis is the part of the root locus or not? So any point on the real axis is the part of root locus if and only if the sum of the open loop poles and zeros on the real axis to the right of the point of interest is an odd number. So any point on the real axis is a part of the root locus. In this real axis, any point is a part of the root locus if and only if total number of poles and zeros on the right side of the point is an odd number. So if I consider any point from 1.00 to plus infinity, then How many poles on the right side? No poles or zeros on the real axis, so 0. So it is an even number. Maybe it is not an odd number. So this part is not a part of the root locus. Now if I consider any point from -1 to +1, it may be -0.5 or +0.5 or 0 or any point in between these two. How many poles or zeros on the right side of this point? Only this pole, 1 on the right side. So any point, if I consider anywhere here, to the right only one pole exists, which is an odd number. So this is the part of the root locus. Any point between -1 and -2, if I consider, for example -1.5, to the right how many poles and zeros exist together? 1, 2. So 2 poles and zeros exist on the right side, which is an even number. So this is not a part of the root locus. Once again this, because 1, 2, 3 poles and zeros together exist on the right side of this point. So it is a part of the root locus. So like this, any point on the real axis is a part of the root locus if and only if total number of poles and zeros on the right side of that point is an odd number. Next, angle of asymptotes and centroid. Now this angle of asymptote or centroid exists only when number of branches, open loop poles and open loop zeros are not equal. If there is a difference in open loop poles and open loop zeros, then only there exist asymptotes and centroid. Because if they are not equal, m is not equal to n, either m minus n will start from open loop poles at infinity, or n minus m zeros branches terminates at 0 at infinity. So in that case, this angle of asymptotes and centroid will exist. So first thing, what is the asymptote? Then the angle. Asymptote is a tangent drawn on the root locus at infinity. So whichever branch terminates at the starts at infinity, to that branch we are drawing a tangent at infinity. That line is called as asymptote. It is a straight line. Angle made by this asymptote with the real axis is called as angle of asymptote. The angle made by the asymptote, that is the tangent drawn to the root locus at infinity on the real axis, is called as angle of asymptote. And this angle of asymptotes phi equal to 2q plus 1 into 180 divided by n difference m. Here n difference m, because n may be larger or m may be larger. Both the cases it is n minus m or m minus n. That is why I given as n difference m. Now this q value you have to vary from q equal to 0, 1, 2 up to n difference m minus 1. Because only n minus m branches starts or terminates at infinity. Now centroid, intersection of all the asymptotes on the real axis is called as centroid. So all the asymptotes, whichever asymptotes and n minus m asymptotes, all those asymptotes where it intersects a common point on the real axis, that point is called as a centroid and is denoted by sigma. And the sigma equal to summation of open loop poles minus summation of open loop zeros divided by n minus m. Summation of open loop pole minus summation of open loop zeros divided by n difference m. Next, breakaway and break-in points. So in the first slide we have seen between -0 and -2 there is some breakaway point. So this break point is a point where two or more branches of the root locus depart from or arrive at that point. Depart from or arrive at that point. Now if we consider this, so in this if we see, this is the point where two branches depart. See, one branch, it starts from the open loop poles and this starts from this open loop poles. But there are no terminating points, no zero exists. So somewhere it will take a deviation, depart. So this point is called as a break point. So what are the possible breakaway points, break points? So one is two consecutive branch open loop poles and in between them is a part of the root locus. So two consecutive open loop poles and between them is a part of the root locus, then there exists one breakaway point because both are starting points, no terminating points. So somewhere in between this it has to deviate. Okay, so this point we need to find. Or one more chance, two consecutive zeros and in between them is a part of the root locus. Then there are also a chance of breakaway point. That is called as break-in points because two branches comes, arrive at this point and then it is going. So one possibility, two consecutive poles and in between them is a part of the root locus. Second possibility, two consecutive zeros and between them is a part of the root locus. Third one, open loop 0 and left of it, entire thing is a part of the root locus. So this is the open loop 0 and to the left of this entire is a part of the root locus, then there exists a breakaway point. So existence of breakaway can be determined from the pole 0 plot, initial plot. So in this case we need to carefully locate the open loop poles and open loop zeros, as well as we need to identify a real part of the S-plane, whether it is a part of the root locus or not. After this we can guess is there existence of breakaway point or not. Now how to find out the breakaway points? So procedure of determining breakaway points. First thing, write the characteristic equation 1 plus g of s h of s equal to 0. Obtain the characteristic equation. Then rearrange characteristic equation and write k in terms of s. K as a function of s, k equal to f of s. By rearranging this characteristic equation, write k as a function of s. Then third step, differentiate expression of k with respect to s and equate to 0. So differentiate this k with respect to s and equate to 0. Roots of dk by ds, this equation dk by ds equal to 0 gives breakaway point, gives possible breakaway points. All are need not be breakaway points, but whether those points are breakaway or not, that is to be validated using angle condition. So whatever the roots we will get for dk by ds equal to 0, those are possible breakaway points, and validate breakaway points using angle condition, which are the valid breakaway points. So like this we have to find breakaway points. Next, intersection with imaginary axis. So in this plot, here it is intersecting. So how to find this intersection? So the intersection of these can be obtained using Routh-Service criteria. So in the Routh-Service criteria, you may get entire row as all the element of a row is equal to 0, then there is a possibility of finding intersection with imaginary axis. So using Routh-Hurwitz criteria, we can find intersection with imaginary axis, this point. Now we will concentrate on rule number 7 and the last rule, angle of departure or arrival. Now if we look at this graph plot, these are the complex poles and these are the complex zeros, open loop zeros and open loop poles. Based on the rule 2, these are the starting points, open loop poles, and these open loop zeros are the terminating point. As this is the starting point and the question arises is at which angle the branch start from this pole. So it may be starts like this, 0 degree, 90 degree, 180 degree or 270 or 359 degree. So there are the possibility of 359 directions. Similarly for this open loop 0, these are the terminating points. There are 359 terminating possibilities. So the angle at which the poles start from this complex pole is called as angle of departure, and the angle at which the branch terminates at this open loop 0 is called as angle of arrival. So we need to find a particular angle at which a branch starts from this open loop poles or the angle at which the branch terminates at this open loop poles. So to find this angle of departure and angle of arrival, the formula is angle of departure at complex poles phi d is equal to 180 minus phi. So for this particular complex pole or this, it is 180 minus phi. Angle of arrival at complex zeros for this, phi a equal to 180 plus phi. Now the question arises, what is this phi is? So where this phi is equal to sigma phi b plus minus sigma phi z. So what is phi p phi z? So sigma phi p is sum of the angles subtended by the phasor drawn to this pole or 0 from other poles. So pole or 0, because it may be applicable to angle of departure or angle of arrival, pole or 0. So phi p is angle subtended by the phasor drawn from the other poles to this pole or 0. That means this angle, this angle, this or this. These are the angles subtended by other poles to this 0, or this angle, this angle, this angle. These are the angles subtended by other poles to this pole. So sum of those angles is sigma phi p. Sigma phi z is sum of the angles subtended by the phasor drawn to this pole or 0 from other zeros. It is like this. So that means, now if I consider for this particular pole, these are the phasor drawn from the poles and zeros to this pole. One line is from this pole, this 0, this pole, and so on. So in this angle and this angle subtended by other poles is sum of this is sigma phi p. Angle subtended by these zeros gives the sigma phi z, sum of these four. Similarly, for a phi angle of arrival for particular complex 0, then phasor can be drawn from all the other poles and zeros, and sum of the angles from the poles gives rise to sigma phi p, and sum of angles made by the zeros gives rise to sigma phi z. So sigma phi p minus sigma phi z gives a phi, and if it is a complex pole, angle of departure is equal to 180 minus pi, and if it is a complex 0, angle of arrival is equal to 180 plus phi. So to construct a root locus, we should follow these 7 rules. Summarizing, first one, root locus is symmetric about real axis. Second one, tells about number of branches, starting point and terminating points. Rule number 3 says about which part of the real axis is the part of the root locus. Fourth rule says about angle of asymptotes and centroid. Rule number 5 says about breakaway and break-in points. Rule number 6 says about intersection with imaginary axis. Rule number 7 and the final one is angle of departure or arrival. So to construct a root locus, we should follow all these rules. So we will solve some numerical in the next session. Thank you.